Hello friends, in this video let us learn about traveling and cogging of induction motor. So if you look at the torque slip characteristics for your induction motor, so here this is your starting torque, this is TS. Starting torque is a torque required when the motor is starting, and this axis represents the torque developed by the motor, and here you are having your slip S is equal to 0, and here slip S is equal to 1, and here slip S than 1. Now the slip is increasing in this direction, slip is increasing here, and the slip is greater than 1 in this region, the slip will be less than 1 in this region. Now these are the two important characteristics shown by the squirrel cage type of induction motor. Now these characteristics are the results of improper functioning of your induction motor. That means either the motor is running at very low speed, or it is not capable of taking load. It is not capable of taking the load. Now the torque slip characteristics, so here you are having T maximum, and this is the normal torque slip characteristics shown by the squirrel cage type of induction motor, and these are the harmonics. This characteristics is due to the harmonics produced by the stator winding. Now we shall discuss this. What are the harmonics here? Now if you see the traveling effect shown by the squirrel cage type of induction motor, so it has been observed that squirrel cage type of motor has a tendency to run at very low speed compared to the synchronous speed ns. The resultant speed is only 1/7 of your synchronous speed. That is, when your motor runs at this very low speed, the effect is known as traveling effect, or you can say the traveling characteristics shown by the squirrel cage type of your induction motor. Now a question arises in our mind, why such type of characteristics occurs in our motor? Now let us see why this occurs. Because this is due to the fact that the flux wave produced by your stator winding is not a pure sine wave. If the flux wave produced by your stator winding is a pure sine wave, then we do not have any kind of harmonics. Now instead it is a complex wave. It is a complex wave consisting of fundamental wave and odd harmonics like third order harmonics, fifth order harmonics, and seventh order harmonics, neglecting the higher order harmonics. Here the odd harmonics will create additional torque fields, and which may be either forward rotating fields or backward rotating fields. The fundamental wave revolves synchronously at synchronous speed ns, where the third harmonic, or you can say the torque field produced by your third harmonic, revolves at the speed of ns/3. Similarly for fifth harmonic, ns/5, and for seventh harmonic, ns/7. So in a balanced three-phase system, the third harmonic is absent. That means the torque developed by the third harmonic cannot be seen in a balanced three-phase system. Now we are remained with the fifth harmonic and seventh harmonic. Now let us see the fifth harmonic current phase difference. If we look at the fifth harmonic is equal to 5 into 120. This gives me 600. So if I take 720 as 2 revolutions minus 120, and when you are going 2 revolutions, the phase difference is 0 and I am remained with minus 120. That means the torque field produced by my third harmonic is backward rotating field. Due to the phase difference of minus 120 degrees. This is 720 degrees minus 120 degrees gives you minus 120 degrees, which is a backward rotating field. Now, if you observe the 7th harmonic current phase difference, 7th harmonic will give us to 7 into 120 and it will be equal to 840. Similarly, we are having 720 plus 120 and we see here we are having the phase difference as positive. This is forward rotating field. Now, the torque produced by the 5th harmonic, which works as a braking action, is very small in quantity and it can be neglected. That means now we are remain with the fundamental wave plus the 7th harmonic. The resultant torque developed by your motor will be equal to fundamental torque plus 7th harmonic torque. The 7th harmonic torque reaches its maximum positive value at high slip with a speed of 1/7 of ns. So, if the mechanical load on the shaft of your induction motor involves constant load torque, if I say this is my constant load torque TL, the torque developed by your motor may not go beyond this load torque. If the mechanical load on the shaft involves constant load torque, the torque developed by your motor may not go beyond this load torque. In this case, the motor will never reach up to its normal speed. If you accelerate the motor, it always rotates at a very low speed, that is 1/7 of the synchronous speed. Now, this phenomena of craveling, the motor travels like this, but it never reaches the synchronous speed. Now, this phenomena is known as the craveling characteristics of your induction motor. So, this is your 7th harmonic. The 7th harmonic like this. This is the resultant torque, and this is the 5th harmonic. 5th harmonic. So the resultant torque will be like this, and if you see, this region is known as the stable region. This is a stable region, and your 5th harmonic is backward rotating field and your 7th harmonic is forward rotating field due to the phases we have seen here. Now, it has been said that for an induction motor, this region is said to be stable and this as unstable. Why this region is said as stable and why this is unstable? Because if you see here, we are having a very low slip, that is, let us say 0 to 10% of slip with a high speed, that is around 90 to 100% of speed. Now, in this region, if you consider your torque is proportional to slip, that is, the torque and the slip are having linear relationship with each other, and this linear relationship helps to calculate the motor parameters to simplify the calculations to a greater extent. Now, when the slip is low and when the torque is proportional to your slip and when it is operating at high speed, the motor settles at a stable position. The motor settles at a stable position, and hence it is known as a stable region for your induction motor. And you can say this is the negative slope, and this adds friction to the motor, and this improves the damping, and this automatically or indirectly increases the stability feature of your motor. This is also known as internal electric damping of your motor. Now, coming to this region, here if you see, due to the low torque, due to TL, the torque developed by the motor decreases where I am maintaining inverse relationship with the slip. That is, as my slip is increasing in this direction, my torque is decreasing. So, if I say here in this region, the slip is around 90 to 100% slip, the speed is 0 to 10% slip. So, when you are maintaining the inverse relationship with the torque, the motor tends to stall in this region. It tends to stall, and the speed is also low in this region, and during the high slip, the motor tends to stall, and hence this region is regarded as an unstable region for your induction motor. So now let us move to the Cogging characteristics of your induction motor. So these characteristics comes into the picture when the motor refuses to start at all. That means there is starting problem occurs in the Cogging characteristics of your induction motor. Sometimes this happens because of low supply voltage. But the main reason for starting problem of your induction motor is because of cogging, where the slots of rotor get locked up with the slots of stator. That is, the slots of the stator slots will get locked with the rotor slots, and your motor refuses to start at all. That means the rotor remains fixed. The rotor is fixed and your motor refuses to start at all. We know that there is a series of slots in both stator and rotor. So if the slots of rotor are equal in number with the slots of stator, they align themselves in such a way that they both face to each other, and when they both face to each other, at this stage the reluctance of the magnetic path is very less, or you can say minimum, and hence the rotor remains fixed and the motor refuses to start, and this characteristics is known as cogging of your induction motor. You can say magnetic teeth locking. So if I draw the slots, of both stator and rotor, if I say these are the stator slots and the rotor slots, what happens is they get locked up together, and this magnetic teeth locking prevents your motor to start. So when the slots of rotor are equal in number with the slots of stator, they align themselves in such a way that they both face to each other, and when they both face to each other, the reluctance of the magnetic path is minimum, and at this point the rotor remains fixed and the motor refuses to start. So this effect is known as cogging of your induction motor. You can say the magnetic teeth locking of your induction motor. Now there is also one more reason for cogging of your induction motor. The other reason is if the harmonic frequencies coincide with the slot frequency due to the harmonics present in the supply voltage. That is, when the harmonic frequencies coincide with the slot frequency due to the harmonics present in the supply voltage, what happens is torque modulation occurs. Torque modulation occurs, and these also causes cogging effect in your induction motor. Now let us see the remedy to overcome the cogging effect of your induction motor. The first remedy is you have to ensure that the number of slots of your rotor should not be equal in number with the stator slots. That means they should not be equal. And the second remedy is the stator, or you can say the stator slots should be skewed in manner. They should be skewed, or you can say the stack of the rotor should be arranged in such a way that they are neither parallel or perpendicular to the axis of rotation. If I say this is the axis of rotation, they should be neither parallel or perpendicular to this axis of rotation, but they should be arranged in a slanted manner like this. And this prevents the magnetic teeth locking, and this automatically prevents the cogging effect of your induction motor. So this is all about the craveling and cogging of your induction motor. I hope you have understood well. Please subscribe to the channel. Thank you.